a quick recap of what we were doing in the last class. We saw the frequency reversal theorem and we are applying it to a practical case of a chopped amplifier. So, let us quickly recall what the frequency reversal theorem is, and while in this picture we show a current excitation and a voltage output. The same thing can be extended to other kinds of inputs and outputs, and one form of the frequency reversal theorem is shown here. So, this will, if you take a network N which is LPTV at Fs and you excite it with e to the j 2 pi f plus m Fs times t, the output at a frequency f will be h minus m of j 2 pi times f plus m Fs times e to the j 2 pi f t plus other terms. Right, and as you know, this number quantifies the ratio of the input at f plus m Fs and output at f. It so turns out, as we have seen in great detail, that if you excite the output port of the adjoint network with a current e to the j 2 pi f t, then the voltage developed here will be h minus m of j 2 pi f plus m f s, right, times e to the j 2 pi f plus m f s times, all right, and this holds for all m, and for the, therefore, if you want to find all h sub minus m of j 2 pi f plus m f s, right, rather than do this one at a time where you keep changing m and measuring what the output is at f, it is much smarter to work with the adjoint network. You excite the output port of the adjoint with your desired output frequency, which is f, and then automatically whatever develops across the input port, when you expand it in a Fourier series, each of those coefficients will give you the h sub minus m of f plus m f s. And and to illustrate one of the applications of this theorem in a practical context, we were looking at chopping, and the idea behind chopping, at least the basic idea behind chopping, is as you all know, it is an attempt to address the problem of flicker noise in amplifiers, and this is the basic signal flow graph. Of course, in practice there is going to be many non-idealities, but right, the idea is that the spectrum of x of t will get translated to around f c and gets processed by the amplifier, where this, remember that this V n, which represents the input referred noise of the amplifier, basically has got a thermal noise floor, but at low frequency it's got flicker noise. and unfortunately the signal bandwidth is also at low frequency. So, this is a big problem as far as the signal to noise ratio is concerned, because the noise spectral density at low frequency is not dominated by thermal effects, but by flicker noise. So, a way to address this is to modulate the input signal to a high frequency, which we call FC, or the chopping frequency, process or amplify the signal at that frequency, where, and this frequency must be chosen clearly, so that at FC and in the neighborhood of FC, the amplifier's noise must be just thermal noise, right. And then once you amplify it, the output is amplified, but still around FC, and then you again multiply it by cosine at FC, so that it comes back to baseband. And as we saw the last time around, this is not enough. There is also unwanted artifacts. I mean, basically the offset and low frequency noise will get shifted to around FC, right, and there is also a 2FC component, right, and all those can be easily eliminated by using a low pass filter. Okay, so this is the amplified signal plus thermal noise only. All right. Now, because this is an LPTV system, right. So, if you, for instance, for instance, if you put this whole thing inside a black box, this is an LPTV system at FC, and we would like to with any, as with any LPTV system, there is always the danger of multiple input frequencies translating to the same output frequency, correct. And our output frequency of interest here is simply the baseband frequency, which is close to DC. So, we would like to understand what all input frequencies can translate to baseband. So, to do that, and we recognize that there are two inputs, and we do not know what frequencies can translate to baseband. So, one way of doing this would be to, for each input, you go on putting FC to 0, FC, 2FC, 3FC, 4FC, and so on until you are blue in the face, and this will take a long time. The smart way to do it is to use the principle of the adjoint network and use frequency reversal. So, this looks like a signal flow graph. So, we can apply what we know about adjoint signal flow graphs, and so we will draw the adjoint. And what do you do about the adjoint? We basically reverse the directions of all the arrows. So, this becomes cos 2 pi minus 2 pi FC times t, which fortunately is the same as cos 2 pi FC into t, because cos is an even function, right. And what do we do here? Well, this is a summing node. So, this becomes the pick off point, right. So, this is V n hat, this is x hat, and the amplifier is turned the other way around, and the multiplier is also turned the other way around, and this again is cos minus 2 pi FC t, which is cos the same as cos 2 pi FC times t, right. And this is the low pass filter is turned the other way around. The bandwidth of the low pass filter is B, right, which is very low frequency, and so this filter also has got a bandwidth B, which is very low frequency, and this is y hat. All right. So, I mean since low frequency and DC are pretty much the same, and we would like to figure out what all components can alias to DC, right, at the output of this whole signal chain. So, what do we do? What should we do? So, this is the adjoint signal flow graph. All right, and what do you think we can do to?
We'll apply the signal at F and we'll find the.
We'll apply the signal at what frequency?
At F only, here it will.
What is F in our case? Baseband, and low frequency is the same as DC. So, we will basically apply DC at the, so you apply DC here, right, and what do we do? I mean, in other words, what we wanted to find are H minus M of j 2 pi 0, because we are interested in H minus M of, yeah. So, H minus M of j 2 pi MFS for both you know FC, sorry, 2 pi FC for both X and Vn. All right. So, so you apply DC here. What do you get here? Let us assume, so this y hat of t is 1, right, and the reason we are applying DC is that our output of interest, output frequency of interest in the original signal flow graph is DC, right. So, if this is 1, what do you get here at the output of the low pass filter? You get 1, right. If you get 1 here, what are you going to get here?
Like cos 2 pi FC.
You get cos 2 pi FCT. If you get cos 2 pi FCT there, what do you expect to see here?
Like
A cos 2 pi FCT, right, and if that is A cos 2 pi FCT, what do you expect to see at x hat?
It's like A cos square.
Yeah, A cos square 2 pi FCT, which is simply nothing but A by 2 times
cos 4 pi FCT
1 plus
1 plus
cos 4 pi FCT. All right. So, as far as the transfer function from x to y in the original signal flow graph is concerned, right, what conclusions can we draw from this analysis?
that H naught will be
H 0
H0
of j 2 pi 0, right, will be
A by 2.
A by 2. So, we knew this already. So, this can also be written as A by 2 times 1 plus half e to the j 4 pi FCT plus half e to the minus 4 pi FCT, right, which means that H minus 2 of j 4 pi FC is,
A by 2.
no, look carefully,
Like A by 4.
it is A by 4, and H plus 2 of j 4 pi FC is also equal to A by 4, right. And the conclusion therefore is that while we knew already that our desired signal is going to get amplified with a gain which is A by 2, right, you also have signals from around plus minus 2 FC which can fold over and will eventually appear like in the same band as the desired signal at the output, right. So, signals from around plus minus 2 FC also appear in the final output. Right. What comment can we make about h sub minus m of j 2 pi m f c for m not equal to 0 and not equal to plus minus 2?
Those will be 0.
They will all be 0. Does that make sense? Okay. All right. So, that so this basically our adjoint analysis has taught us that we have to be careful about input signals which are around multiples of which are around 2fc, because they that can also get translated to baseband, and the mechanism actually quite I mean, once you think about it, if you once you know the answer, it is easy to intuitively see why. So, if you have an input here which is at 2fc, when you multiply it by cos 2 pi fc, it will also translate to, there will be one component at 3fc and there will be a component at 2 at fc, right. That fc component will get amplified through the amplifier, and then a part of that will get demodulated to, half of it will come to DC, another half of it will go to 2fc, right. So, and that is what you are seeing at the output. Now, what comment can we make about the transfer functions from I mean, what all components of the amplifier's noise will translate to DC at the output? Well, to see that, we just look at the signal that is appearing at V n hat, and that is A cos 2 pi f c t, which can be written, it can be expressed as A by 2 times e to the j 2 pi f c t plus e to the minus j 2 pi f c t, correct. So, as far as the amplifier noise transfer function is concerned, what do you see? Well, h, what comment can we make about h 0 of j 2 pi 0?
0 is 0.
Is 0, and does that make intuitive sense?
We are not giving, there is no.
Why does it make intuitive sense? So, basically this is saying that if you I mean, what does this mean in English? It means that if V n is DC, right, the output is
0.
0, and why does that make sense?
We are,
If you put in DC, what is happening?
because on average it is becoming 0. Because
Yeah.
of that.
So, basically the DC is getting amplified, but then it is getting modulated to the chopping frequency and is subsequently getting eliminated by the low pass filter, right. So, that is why it makes sense that h 0 of j 2 pi 0 is 0, right. Now, what comment can we make about h plus minus 1 of j 2 pi f c? Just I mean, I think h, sorry, this h 2 of must be h minus 2 of, and this must be minus, yeah. So, h 1 or h minus 1 of j 2 pi f c is
It's like A by 2.
a by 2, and similarly h
Plus
1 of minus j 2 pi f c is also a by 2. Now, what is this telling us? That if the input has got some frequency components around f c,
we will have a
they will get translated to will appear at DC in the final output, right, and that makes sense, right, because if this has got a if V n has got a component at Fc, right. Fc is getting amplified to the amplifier and getting demodulated by the output multiplier, and you just see, correct. But we know that at, I mean by definition we know that there is, I mean that is only thermal noise there, right. So, thermal noise from around Fc is going to appear in the final output at DC, right. Okay. So, this is you know an example of using the advantage of using adjoint signal flow graphs, right. Now, let me do a little more complicated example. Now, except that I mean remember, this is okay for a block diagram, but in practice there are many difficulties with trying to implement such a scheme. One is, you know, how do you multiply x of t with cos 2 pi f c t, right. Okay. It is much easier to. So, what is done in practice is the following.